In this video, we're going to look at a well-known concept from computer science called currying. And of course, we're going to look at it from the perspective of category theory. And we're going to show how it's actually an example of a co-universal. So we've already looked at co-universals. It's the dual concept to a universal. And we're going to also see that this specific type of co-universal has a specific name. So you might think of it as the next categorical construct in the list that we've been looking at so far. And that's called an exponential. So this is, in this case, the categorical exponential. So what is currying? Well, we have the definition right here. Currying is using a function of two or more variables to uniquely define a function of the first variable, which returns a function of the second or of the rest. So here we have it phrased both in the binary case and the case where we have a function of more than two variables, which would then return a function of not just the second, but of all of the rest of the variables. But in this video, we're just going to focus on the binary case. So that is functions of two variables and how currying works in that case. Obviously, the concept extends to functions of more than just two variables, but we're going to look at the two variable case as a sort of first exploration. So what would this mean, to use a function of two variables to uniquely define a function of the first variable, which returns a function of the second? Well, right now we're going to talk from the perspective of computer science. So we'll just look at it as, say, a function f, which goes from a cross b. So it has two variables as inputs. So an element of a cross b, and returns some element of c or of type c, depending on how you want to think of it. And so what does this mean? We need to be able to uniquely define a function of the first variable. So maybe I'll call it f tilde, or the curried version of f, which takes in just the first variable as an input, right? So a was the first variable, so it takes in a, and returns a function of the second variable. So that is a function going into C from B. So the set C superscript B just corresponds to the set of all functions going from B into C. So this is what we would need. We would need for any f to be able to define f tilde. So what would this look like? Well, you'd have f tilde of a would need to give you some function going from B into C. And we'd need to have that f tilde applied to A applied to any B, right? Because this is a function that takes in B as input, would have to be equal to f of AB, right? So this is what we would need in order to be able to uniquely define it. Let's look at a quick example to make this a bit clearer. So let's say in this case that the function f is actually the multiplication function. So mult goes from, let's say it's multiplication defined on the integers. So it goes from integers cross integers. I take in two integers and I return an integer, and it's just defined by, as everybody expected, multiply of x and y gives you x times y. Well, we can use this function of two input variables to define the curried version of multiplication, which we might call multiply by, which takes in the first variable, which is the integers, and returns a function from the integers to the integers, which corresponds to multiply by, which goes multiply by x, sorry. So multiply by of x gives us multiply by x back. So this is a function now, multiply by x, which this one goes from the integers into the integers, right? We need it to return something of this type. And it's defined, as we know, by multiply by x of some y is equal to x times y, which obviously is equal to multiply of x and y. So we can see this is an example where a, b, and c are all the same. They're all the integers. And so we have a function multiply, which takes in two input variables. And we can curry that function. And that's a function that we call multiply by, which give me any integer x, just like if you say give me any a and a here, and I'll give you back a function going from b into c, or in this case going from the integers to the integers, which in this case is multiply by x. And we're going to define it so that multiply by x of y has to give us back the same thing that multiply x and y gave us, right? So this is like multiply by x. This could also be written like this, multiply by x applied to y, right? That looks a little bit more like this form is equal to multiply x and y. So this is currying applied to multiplication, simple old multiplication. And the important thing to note is that this curried version is well defined. If you give me any input x, so give me any integer, I can only give you back specifically the function multiply by that x. And so what that means is that basically, if we evaluate multiply by x for any integer y, we have to get back x times y, or mult xy. So it's completely determined, and that means this function here is well defined. So how do we start to translate this into the language of category theory? Well, let's start by drawing things out. So what we're saying is now if we have some morphism f going from A cross B, which is now just an object in the category, right? Maybe some category C, let's say. If we have some morphism f going from A cross B into C, then what we must have is that there must be some unique morphism f tilde going from A into C superscript B, which now we're talking about categories, so we're losing the concept of elements. So now this is just another object in the category. It has nothing to do with morphisms on anything. It's just, we know under the hood it does when we're talking about functions. But since this is the categorical perspective, this is just another object in the category C. Well, what we need to have is that there exists a unique f tilde here going from A into C superscript B, such that what? Well, when we're talking about sets and functions, it's such that if you give me any input A to my curry function here, the resulting function that I give you back, if I evaluate that function on any input B in B, I need to get back my original FAB. But we're looking from a categorical perspective now. So I'm not really allowed to say elements of this as inputs to functions of that, right? That's not allowed in categorical terms. So instead, how can I express this statement? Well, I can sort of just force the evaluation function, right? I can define an evaluation function that just takes in things like this, elements of the functions going from B into C. So this goes from C superscript B, and takes in these input elements, right? So it takes in a function going from B into C, and an input B, and just gives me back the result in C, right? So that's pretty obvious. It's just E applied to, say, like H going from B into C, and B in B will just give you back H of B, right? So if we do that, well, we can say that if we're evaluating with the evaluation function combinations of C superscript B and B, then what do we need? Well, to force this condition, we need that the evaluation function applied to f tilde of A and B, right? The evaluation function applied to the combination of f tilde A and B needs to correspond to our original FAB here to make it equivalent to this condition. But we're still talking about elements, right? The inputs A and B corresponding to F applied to A and B. So how can we maybe remove those? Well, we can notice that this is the same as F tilde cross 1B applied to AB, right? So the A will have F tilde applied to it, and then the B will have 1B applied to it and give us back B. And this needs to be equal to FAB. And if that's the case, then we can say that the evaluation function after F tilde cross 1B is equal to, and all of this applied to AB is equal to FAB. And now we can remove the AB, right? Because it's for an arbitrary A and for an arbitrary B. So we can say that the evaluation function after F tilde cross 1B is equal to F. And so that's sort of very convenient because that also fills in this commutativity square, right? We're going from A cross B, and we're going by F tilde cross 1B. And when we do that, we get back that the evaluation function after F tilde cross 1B is the same as F, right? We get this commutativity square. So this is starting to look very, very familiar, and it's starting to look very, very convenient for what we're trying to show. Why is that? Well, because this is starting to look very much like a co-universal pattern, or the diagram for a co-universal. So what are we missing? If we wanted to say that the evaluation function along with C superscript B cross B together form a co-universal pair, what would we be missing? We would be missing what functor it is applying to, right? In order to have a co-universal property, we need a functor that it's defined for. So what would be the functor in this case? Maybe pause the video here and do that as an exercise. What is the functor that goes, maybe we can call it P. What does P look like? How do you define P? Well, P is a functor going from the category C into the category C. And how is it transforming the objects? So what is P of X? Well, it's giving us back the object cross B, right? So we could just say X cross B. And how is it transforming the morphisms? Well, it's taking, say, H in C and giving back H cross 1B. right? And so hopefully when you define this, firstly, hopefully this is how you defined it. And secondly, hopefully you also proved that this is a well-defined functor. If you didn't, then pause the video again and show that now. Make sure that this functor is well-defined. So what does that mean? Well, identities need to map to identities and compositions need to map to compositions, right? So you can check that now if you haven't. And with that, we have everything in our co-universal diagram here defined, so we can try to write it out. So this is basically the categorical version of the discussion we just had about currying, which is that C superscript B and the evaluation morphism going from C superscript B cross B into C is co-universal for C here and the functor P. And so this particular form of co-universal actually has a name, so you can think of it as the next categorical construct on the list that we've been looking at so far, and this name is the exponential. So to explicitly define it based on this definition here, we can say that if C is a category with binary products, then the exponential of B with C is the pair C superscript B, where this is just an object in C, and the evaluation map, which goes from C superscript B cross B into C. Then for any F going from X cross B, so for any X, if we have an F going from X cross B into C, in this case, X was A here, then there needs to be a unique F tilde or curried version of F, which satisfies this equation. The evaluation map after F tilde cross 1B here from X cross B into C superscript B cross B, which basically says if we evaluate the curried version of the function by the inputs and do that across all the inputs, they always have to correspond to what F assigns it to. But that's obviously thinking in terms of functions, because here we don't have elements or functions on elements or anything like that. So if that's the case, then we have an exponential, and we call this, as we've been calling it the whole time, the evaluation map. And this curried version of F, or F tilde that we've been talking about, we call the transpose or the exponential transpose of F. Now, of course, as with the other categorical constructions that we've looked at, there's no guarantee that any pair of objects B and C will have an exponential within that category. You need to find objects and morphisms which satisfy the definition here. But in case every single pair of objects in your category does have an exponential, or even more than two objects, obviously we said we were going to focus on the binary case, but this can be expanded. But if any pair B and C in your category have an exponential, then you can say that your category has exponentials. So, for example, we just saw that set has exponentials. And the reason for that is the whole discussion that we just had when we were still thinking of them as set functions, right? I could apply A and B as elements or inputs because they're functions, right? And I could make the argument based on the elements of the function and working out the algebra here. So, but in a general category, we don't know whether this equation is going to be satisfied or not, and satisfied in a unique way as well, right? There needs to be a unique F tilde here, or a unique transpose. And so there definitely are categories where exponentials will not exist. And so let's look at one example now. So if we look at the category group of all groups, and for this example, we'll set X to be equal to the trivial group, which just contains one element, which is the unity 1. And we're going to assign both B and C to the same group G. And that can be any group. So we have the trivial group cross some random group G. And what we want to say is, for any F going from that domain into the group G, any group homomorphism F going from 1 cross G into G, we need to find a unique mediating morphism here, F tilde for F, which goes from the trivial group into the group of automorphisms, right? So we're good here because this is a group. If we take all of the group homomorphisms from G to itself, that forms a group under composition. And we've seen videos kind of like that in the past. And so what is the issue here? Why can we not find this F tilde? It's maybe a little bit of a tricky exercise, but you could try pausing here and thinking about it for a second. Well, the first thing to notice is how many ways are there to define F tilde? There's only one, right? Maybe that's another exercise. Pause the video here and ask yourself, why is there only one way to define F tilde? Well, because there's only one element in the domain, and not only that, but it's the unity. So it only needs to map one element, and we already know what element it needs to map to. It needs to map to the unity of this group, which is obviously the identity on G, right? The identity homomorphism on G, or automorphism. So there's only one way to define F tilde. Well, if there's only one way to define F tilde, there better only be one way to define F. Because if there's more than one different F, we're never going to be able to satisfy all the different F's with only one option on this side, right? But of course, any automorphism going from G to G will define an F here. Because if G is any automorphism going from G to G, I can always define an F by 1G just gets mapped to G, right? That's clearly going to give me a group homomorphism going from 1 cross G into G. If you don't believe me, pause the video here and do that as an exercise. Does this define a group homomorphism F from 1 cross G into G or not? But I'll give you a hint, it does. And so that means that as long as we have more than one automorphism going from G to G, we'll never be able to satisfy it with just a single group homomorphism F tilde, right? We won't be able to find an F tilde for every single F. So all we would need to find to show that the category group does not have exponentials would be to find a group with more than one automorphism, right? And there's lots of groups with more than one automorphism. So we can say confidently that this co-universal property does not apply in group, and so there are not necessarily exponentials for any two groups in the category group, and that means we can't systematically apply currying in the category of groups. And that pretty much concludes our discussion, but I just wanted to mention before ending the video that currying is named after Haskell Curry, who was an American logician, and he actually has quite a few different things named after him. He has currying here, he has Haskell, the functional programming language, and there's also the Curry-Howard-Lambeck correspondence, which reveals a deep and fundamental connection between logic and proofs, functional programs or typed lambda calculus, and certain types of categories. So I wish I could say I understood all that in detail, but seems like he was quite prolific, so somebody worth looking into a bit more.